And hello, welcome back. So today we're going to talk about a little bit about continue the discussion on the case setup. So in the last video we talked about fvSolutions, and okay, over here we talk about this is a periodic basis, but we already talked about that. So let's just continue. And how do we set the flow? Again, we use this mean velocity force. Okay, this is a function object that gives us ability to control the velocity, the mean velocity. Okay, so it'll be a momentum source. It will not be in the boundary condition. So actually, this actually gives the whole fluid some force that so that the mean velocity can be fixed. It's very useful for channel flow. Okay, so okay, so the cyclic conditions, they help, but in your just one note that in your pressure, what do you call that, pressure file, your pressure file, okay, normally you will see a lot of calculated values here, but when the boundary condition is cyclic, you have to put it as cyclic. Okay, so one important question, actually, if you think about it, one important question is this: you have a cyclic boundary condition, let's say between top and bottom. Your gravity is going this way, then you have a cyclic or periodic boundary condition. So let's say the pressure here is 1 times 10 to the 5 pascals. Over here, your pressure may be 1 times 10 to the, or 2 times 10 to the 5, right? 2 times 10 to the power of 5 because of hydrostatic and whatever other reason, right? So if this is cyclic, won't it be like, okay, if this is 2 times 10 to the 5, am I going to pass this pressure onto here, 2 times 10 to the power of 5? Okay, and then won't that cause like an infinite pressure buildup? If you think about it, 2 times 10 to the power of 5 will be replacing the value here, and then here you have 3 times 10 to the power of 5. 3 times 10 to the power of 5 in the next iteration will be, going on top, and then at the bottom you have to have 4 times 10 to the power of 5. So your pressure just keeps building up infinitely. So good thing is that this doesn't happen in the cyclic boundary conditions. You don't have to worry about that. And what you must give is a reference pressure. What you must give instead is a reference pressure in the FV solution file. Okay, so FV solution file, you'll see a pressure reference cell and a pressure reference value. It means that it fixes the pressure at, for example, cell 0, I think, at 1 times 10 to the power of 5 Pascal. Okay, so that's what you're doing there. You're fixing that pressure. Everything else in the whole fluid, or the whole fluid, it will take reference from this pressure cell. This cell. So you don't really have to worry about this infinite thing going on. You don't need to worry about boundary conditions in that sense. So yeah, that's one thing that you don't have to worry about. So for this channel flow, so I'll just skip a lot of this, but the mean velocity force, that's a very useful thing to use for the, what do you call it? Okay, so it's a very good thing to use to set the velocity of the flow. And where you will find that is, okay, you will look at heat transfer, or not heat transfer, incompressible, then pimple foam. Okay, you go to LES, you go to channel 395, and you look at the constant FV options, right? You have this mean velocity force here. This is actually perfect. You should use this to set this momentum, and some of the guides you can see here. Otherwise, we already gone through that. So next thing I want to talk about is data collection. Alright, so how do we collect the data? How do we sample data every time step, right? Because as you run simulation, you will have collected a lot of data. For example, you have all these time files, which you kind of want to get rid of because they contain lots of redundant data and they'll take up lots of disk space, especially when your mesh size is huge. Some of these files folders, for example, let's see, for example, your velocity folder, this can actually be as large as a few gigabytes if you're talking about a DNS case. So ls, lh, this is for size, to make the size. You see that in the LES case, these are still pretty manageable, a few megabytes a piece. But when you talk about DNS, this will get exponentially bigger because there's a huge number of cells you have to deal with. So one of the ways to deal with this is firstly, in this thing, use this thing called purge write. Purge write. This setting here actually tells you how many right. If you set it at 0, it means that it does not purge anything at all. If you set it as any number rather than 0, that means it will just keep the last whatever number you specify here. For example, if you specify the purge write number here as 5, it will just keep the last 5 time steps. Everything else it will delete. Okay, so that will help you save some disk space. Alright, and of course the functions you want to have, they are there to help you sample things. So there are some custom FV options you can use. These ones are actually here to calculate the mean velocity profile and of course the deviation, which you see here, prime to mean. The deviation of these velocity profiles, okay, they will calculate throughout all the time step, and it's a mean based on the simulation time. So this is one of the functions you can use to develop your mean velocity, but this doesn't give you, this is still way too much information. So therefore, what you might want to do is this. Okay, CD, and you go to one of my reference folders. You can find all these inside your tutorial folder, and you can take a look at the buoyant cavity. You take a look at the system, and you see the sample file here. This sample. Okay, this will tell you, okay, what you're seeing here is, okay, these are functions that help you to sample data across a line. So let's say you want the data from here to here. You want the temperature profile, right? So you have a plate 1 at 100 degrees C, plate 2 at 40 degrees C. So you want to sample temperature along this line from 100 to 40, so that you can have a TX graph, right? You have a T versus X. So that's what you want. How do we do it? This is how you do it. They use this sample function. It says type sets, library sampling, blah 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 blah. So what is this saying? This is a set. It's a function object which you can execute whether at the end of the simulation or you can run it in real time. Okay, so it will have some library you need to give it. So this one's just copy and paste. These pieces just copy and paste. What you want to pay attention to is this sets over here. It will tell you, where your data is sampled. For example, this one, you say the type is face. So what is this typeface talking about? So there's a lot of cells in here. When you want to sample data across a line, you'll actually be crossing a lot of the cells. So what actually we do is that whenever the line meets the cell face, it will take the value of t here, and then when it meets another cell face, I'll take the value of t here. That's what when you have the intersection between the line that you have and the face, then you get your data point. So the axis, okay, over here they use x, which means that they will only display the x coordinate. All right, if you want all three coordinates, for example, you want the x, y, and z coordinate, you just type x, y, z here, like so. If you want to have a display of the x, y, and z coordinates printed up, you just type x, y, and z here. Otherwise, you just type x. And the other alternative is that you write the distance here. You can label the axis as distance, so that instead of using the x, y, and z coordinates, you can say, okay, here the start point is 0, here the distance is L, so that your axis is actually somewhere in between 0 and L. It is the value of the distance. Okay, let's say you have this point here. Okay, so this is the temperature, but what is it measured against? It is measured against the distance from here to here. Right, so it's a distance. So instead of plotting t against the x coordinate, so to speak, you plot it against the distance from this start point. Okay, so yeah, that is one thing. The other way you can talk about you can actually sample data is, instead of using the face data, you can actually also define that, okay, I want a line going from here to here. All right, I want a line going from here to here, and I want to have, let's say, 100 points here. Okay, 100 points. Okay, so this is your other way of defining it, and I can show you the code in a little while. But this is the idea of how you can sample t and u data, temperature and velocity data, across the whole thing. Okay, so I'll do it every 4 seconds. So I want to run it actually in real time instead of having it at the end of the whole simulation. Okay, so that as I delete those old data files which are very big, temperature, velocity, whatever data file, which may be huge, I want to actually print out summarized data plots of temperature versus the distance, or velocity versus distance. So I'll show you how to do that in a little while. Okay, and mainly it's to do these function objects. And also, if you want to calculate heat transfer coefficient and let's say the wall shear stress, because you want to calculate the friction velocity, you can also use this thing called function objects. Okay, some function objects are wall shear stress and therefore heat transfer coefficient. Okay, so let's take a look at the actual case, and I'll show you the function objects that I used. QA here, quit everything, and this should be available on GitHub after the video is over. I mean, after I'm done with the simulation anyhow, so it'll take a while to upload. Anyway, so this is an example of the case we developed using the top processors there. I'll run you through them. So first thing first, like promised earlier, we want to take a look at the some of the function objects. We want to take a look at some of the function objects, and usually you put them in the control dictionary. So what does my control dictionary look like? I said the application is born in PimpleFoam, which is very useful when I talk about my all run scripts. Okay, it starts from the latest time and it ends at 100 seconds. Okay, so of course I can actually change this to something else to my convenience, but I'm not going to do that now. Delta T, as explained earlier, 2 times 10 to the minus 4. Adjustable runtime, yes, is the right control. Basically, there will be, adjustable runtime means that OpenFOAM will dynamically change the time step to adjust your time step so that it will fit some certain Courant number, CFL number. So write interval is 0.4, so every 0.4 seconds it will write. That's how these two actually come hand in hand. Purge write 10, meaning to say I keep 10 data points, 10 time steps. Everything before 10 time steps I delete. Okay, these ones are the same, I'm not going to talk too much. Runtime modifiable true, meaning to say that if I change the control dictionary halfway during the run, we can do that to change the settings. But more importantly, adjust time step is yes, you have to say it's a yes, and the max current number that we adjust the time step to is 0.5, which is what we want. Okay, so what are these function objects? Okay, first, field average. This will give you the velocity and pressure mean fields, as well as this thing called prime to mean. This is actually the RMS value, which is okay. On average, if let's say you have instantaneous velocity like this, so okay, across time, because we use a time average here, you have instantaneous velocity like so, and we have a statistical deviation from this mean. All right, this is actually u prime, because u prime equals to u minus u bar, but we want the root mean square, right? So we have a root mean square here, so that's the RMS value of this. So we square it and then we take a square root, the positive square root. It will give us an average deviation over time of this u velocity. So you need to repeat for x, y, and z, and that's what this u mean is. Pretty useful, but I didn't quite think too much about it, because I rather just select the data manually. But these are useful tools, so I kind of just left the code there. Now, the other thing is that, okay, I have this heat transfer coefficient calculations. So I have one side for the left wall, the hot wall, and it's going to calculate a wall heat flux, average wall heat flux, and then of course you need to divide it by some temperature difference. So what the temperature difference is, it's basically the wall temperature, and then you have to take it, a difference between that and some fluid temperature, usually T infinity, because Q or H equals to Q over T S minus T infinity, right? So usually TS will be the wall temperature. T infinity you have to specify it yourself, and that is actually what I'm doing here. I'm specifying that this reference temperature is actually 343 Kelvin, or about 70 degrees C. So here it says I'm using a heat transfer coefficient function object, and every time that you write a time step, I will execute this function so that it will tell me the heat transfer coefficient. Okay, so which wall is it doing? Which patch is it doing? I'll say it's the left wall. Okay, I didn't show you the block mesh yet. And it's going to take the field, temperature field, to help you, determine which your heat transfer coefficient. I think I don't know whether this is necessary. You have to go and double check. But anyway, this is what I have, and it works. Heat transfer coefficient model is based on fixed reference temperature, so that's what it's saying here, and the reference temperature is 343 Kelvin. Same thing for the right hand side. Although of course you can actually lump these two together, the left wall and right wall, meaning to say if I write, okay, I can actually just write this here like that, because I want heat transfer coefficient at both walls. I can write it something like that and it'll still be okay, but for now, for demonstration purpose, I'll just keep it separate, so that in case there are any bugs that come up, I know where they come from. So I rather write it in a standard way, where the code allows you to write, rather than write it in a more complicated format, and when error comes, I don't know where it comes from. So this is one of the reasons why you can't write it simply first. Okay. Second thing, of course, this function tells us the localized wall shear stress, right? Okay, so this actually calculates the heat transfer coefficient at every single cell. This one calculates the wall shear stress at every single cell. Of course, these data will be deleted, so what I want to do is, instead of leaving it inside the time directories, for example, 0 seconds, 2 seconds, 40 seconds, etc., I want to take an average, and when I execute this function, it will be written into a separate file so that it does not get deleted when the purge write command is executed. So this is an average value, and what it does is that it will do a surface average. Okay, so you use this type surface field value with these libraries, and what do I want to average? I want to average the heat transfer coefficient T, the wall shear stress, and of course the wall temperature. Of course, it's kind of redundant to talk about wall temperature, but I mean, having this wall temperature, it helps you to know, if you put it in the same file, it helps you to know which wall you're talking about. Is it the hot wall or the cold wall, right? And the region type is called patch, name is right wall, meaning to say I'm taking all these surface average values on the right wall, okay, which is the wall that is colder. I would say that the left wall is 100 degrees C, right wall is 40 degrees C, and I do an area average. So this is what the file looks like, and I repeat for the left hand side, and of course the velocity. Okay, this is the velocity and temperature sampling. So what I said here was the type sets. All of these things we copy and paste from the sample file. So there are two so-called sets of data I want. So this is what this highlighted part is talking about. One is called this phase line intersection, where again we talked about the type phase, and the axis, instead of x I use y, and you give it the start and the end coordinates. Alright, so this is somewhere in the middle of the plate, so I can show you the block mesh later on, maybe in the next video. And this is the end. Alright, so this is the one where it says every time the line that you are drawing between the start point here and the end point here, every time it meets the face of a cell, you take the data over there. So that's how it's done. Of course, you can have uniform points as well. So for example, we say this is type uniform, and the axis is distance. So much like I was talking about just now about the distance. Same start and end points, but instead of having it at every phase, I say maybe the number of points is like 300, give or take, something like that. So anytime it's there, you'll probably just interpolate between two cell faces. That's all. And the fields given are T and U, temperature and velocity. So this is how we set up the function objects file and the control dig file. Okay, so what I do is that I run a Reynolds average Navier-Stokes case first, because that's the easiest and the fastest, so you can debug very quickly. And then we move up in terms of mesh refinement to IDDES, and use that as a starting field for DNS. That's the basic idea. So thanks for watching. I'll see you guys again. I'll talk more about how the case is structured. Okay, bye.